Okay, Assalamu alaikum, good evening and good afternoon, everyone. আপনাদের I don't know, সাদার্ন ক্যালিফোর্নিয়াতে কি অবস্থা সবার এখানে? কে আসছে
খুবই
আমাদের?
গরম এই আর কি।
আচ্ছা আচ্ছা ঠিক আছে, তো we're not gonna take too much time since we already had our first session yesterday. Amin taught the semiconductor processing class yesterday. That was great. Thank you, Amin. And other students we have here, Junayat is here, Ridwan is here. Um, so let's see, Nabil is here. So I want to, before we start today's topic is microelectronics and PCB. Before we start, I would like to hear from the students a little bit, like, is there any prior experience you have with the microelectronics, or it's going to be kind of like your first time hearing about microelectronics? Is Can I know from anybody would like to share?
Hi. Actually, that'll be my first time to know about this.
Microelectronics.
I don't have any. Yeah.
Okay, okay. All right, great. Okay, so that sounds good. Yeah. Now I will share the slides, and as we go along, please ask any question. Um, and I will stop, and I'll try to make sure that whatever we are covering today, at least, even if the topic is not so many, but whatever we cover, at least we are able to give you guys the idea, basic ideas, and you take away something really concrete, knowledge about these topics. Okay. So that would be my goal as an instructor today. And thank you for joining. So let me share. Um, okay, are you able to see my slides? Everyone, can you see my slides?
We can see the
Yeah.
slide, yeah.
Okay, okay, all right. Yeah, if you can just do a thumbs up if you want, yeah, if you have problem speaking, that's okay too. All right, so a little bit about the course. So this is our first time we're teaching the hardware engineering course through our AABEA Silicon Valley. Thanks to all my teammates in here in San Jose and also in LA. Everybody together, we worked hard to make this happen. So thanks to all the EC members, board members, advisors. And so a little bit about me. I'm currently a design engineer and also a TPM in the AI and compute server engineering group in Hive. And before this, I worked in Intel, Broadcom, Seagate, startups, and I have more than almost 15 years of experience in the hardware industry in the Silicon Valley and also in, Irvine, which is part of Southern California. I was there for almost 5 years in Broadcom. So you can read about me, and if you have any questions, send it to me in the email. And this is my LinkedIn also. Once I am done with this course, I will share my contact information and also the LinkedIn. If you have any more question, I will be very happy to answer later on as well. Okay. So okay, so let's talk about what we are going to cover today. So we want to know what the microelectronics is and some of the basic application. And once we know what those components were, we want to know like how they function, right? In very high level. The circuit could be complicated, but we won't go to that. But hopefully, inshallah, next time when we teach this course again, we'll go more details. Uh, we'll talk about the resistor circuit, which is a resistor is one of the most common component in a microelectronics. So we'll talk about that a little bit. And then circuit analysis, right? Well, when we have a circuit, there are certain laws like Ohm's law, Kirchhoff's voltage law, KVL, KCL, Kirchhoff's current law. We will briefly talk about that. And mm, okay, there another meeting. Sorry. Ah, okay. And then I summarized some 9 equations that we can remember together, which will help us later on to understand the electronics um, theory a little bit better. And then we talk about just a very little bit about the PCB design because I personally feel that without understanding, the microelectronics properly, it's pretty hard to understand the design itself, right? So, but as we go along, we'll have more of these classes, right? So we'll cover slowly one after the other. So first of all, what is microelectronics? So from the name itself, right, you can understand electronics, micro, right? So we're talking about the very tiny components here. The components are very small. They're so small that they could be at the size of micro, which is 10 to the negative 6, or the nano, 10 to the negative 9, right? Very, very tiny components. And some example. So if you remember yesterday's class, you already hear about diode and transistor, right? So those are some component of microelectronics, and there's some more like resistor, capacitor, and inductor, all those, right? So there's some difference between each of these, right? But there's a major difference in category of microelectronics is that some are passive, some are active. So what you heard yesterday from Amin's lecture, he talked about diode, he talked about MOSFET, right? So those are more like an active microelectronic device, right? And today I'm talking about the passive ones. So what are the difference? So difference between active and passive components is mainly one, and that is that, level of power source they need. So for the resistor, transistor, uh, there's you don't need the power source for them to have a kind of like a energy to be stored. They can have energy stored without any power source. Whereas for the diode and the transistor, the power source is necessary, right? And so we can talk more of the category of microelectronics later, but today's lecture will focus mostly on the passive components, right? And those are like resistor, capacitor, those. And what are the applications? Where we use microelectronics, right? That would be a very interesting thing for us to know. Any thing that comes to your mind? Anybody want to volunteer? Where we see microelectronics, like where we see this resistor, capacitor in our daily things that we use. Can you tell me like anything like that we use daily that has resistor, capacitor?
Yeah, of course. I think that was like a fan. Of course, have
You say phone?
a fan also.
Yeah,
It,
yeah. So it could be anything. For example,
yeah.
the phones we use, the TV we use, our
Hmm.
computers we use, everything has this, right? Everything has
Yeah.
resistors, everything has capacitor. So just
Hmm.
about anything, right? Just about anything will have these components. Okay. So more into that. So these are some pictures. This is how the resistor look like. This is how the capacitor look like. Inductors look like. And then we have the IC, which is the integrated circuit, right? Inside each of the integrated circuit, which is active, right? Active microelectronic device. There's a lot of things happening, right? And then you see diode, right? Which you learned yesterday. So these are some example. And I like to talk about like with this, what do they do, right? Like before we even get into what they are, I want to understand that, okay, when we are doing using the resistor, when we are using the capacitor, what exactly we are measuring, right? We are measuring some voltage, right? Voltage is the difference between electronic charge, basically. And when you have that difference in charge, there is some energy difference, right? Potential difference. And that's how the voltage is we measure, right? That's the definition of voltage from one point to another point. When you have some current flowing, there is some change in the electrons, right? That is passing through, and that difference would create some voltage. And then we have current. So how do we measure the voltage? Voltage, in short, we'll write it as V, and the unit for voltage is volt, right? Kind of makes sense, right? At least to me, it makes sense. And then current, what is current? Current is measured in ampere, right? In short, we call it amp, right? You hear a lot like, oh, this is 2 amps, 3 amps, 4 amps, like that. And in voltage also, for example, when you buy the batteries, right? I don't know if you know it. We say, hey, we want to buy a AA battery. But do you know what is the AA battery? It is actually 1.5 volt, right? And then we have those batteries that we use in our remote control, right? The cars, when you play with the remote cars and everything, those are the 9 volt one, little square, you know? So that's how, the measurement of voltage and the current plays in role in our daily life. You see it from the batteries, right? And then power, what is power? Power is measured in watt, and we'll talk about a little bit more later how the power is calculated using the voltage and the current, right? And then we already talked about the resistance. We'll hear more about the resistance, capacitance, and all that. But this slide is mainly for you to understand what is the unit, right? Measurement unit. We use the word ohms, right? It's a Greek letter ohm, as you see. And property that the resistor carries, that is called resistance, right? And then capacitor has that property that's called capacitance, and it is measured in farad. It's after the name of a scientist, and we call it a F. Inductance is measured in Henry. It's also named after the scientist, and in short, we write it as L, which is kind of, you have to remember it's not I, right? Inductance is L, and when you have the unit, it is Henry, right? And in short, the unit you write as H. And then charge. When we talk about the potential difference, voltage, we're always talking about the charge, right? Electrons. And the charge, how do you say it? Sometimes you will see E or P or N, right? But in general, when you're just talking about any charge, regardless of whether it's a positive or negative, you can say it as a Q, okay? And the unit for that is coulombs. And then we have the energy. Energy is a little bit different than power. It's not same, okay? And that is measured in, we call it a U, right? Like for the energy. And the unit is joules. It's not watt. When you hear the PG&E is calling us and saying like, okay, this many, watts being used and this, that means they're talking about the power. And what's the main difference in energy and power? We'll talk about that later, okay? Any question on the unit and the notation? I think it's pretty okay once you read it, right? Should be okay to understand. Okay. So let's now talk about the resistor. What is resistor? What is capacitor? What is inductor, right? The resistor resists, right? Kind of makes sense. Yeah, when you hear the word, that's how I used to remember when I was in high school. By the way, I did my high school from here also in Georgia, Central Gwinnett High School. I went to in Atlanta, Georgia. So this is how I would remember my resistor. Resistor, resist current flow. Okay. And capacitor, yeah, even though the name doesn't explain that much of what it's doing, but we have to remember that it will store and release the energy. And the way it does is, does it do it in the form of current or in the voltage? It does in the form of voltage. Okay, so that's something to remember about the capacitor. So you can think of capacitor as a, this is how I would remember. Okay, and I'm telling you my thought process, but everyone has their thought process of remembering something. Capacity, right? Capacity means how much can it is capable of holding. So that's how I remember. Oh, storage, it stores the energy. Capacity, that's the word capacitor, right? And then comes the inductor. Inductor is kind of like, you can think of it as a, sort of like a resistor, but it is actually opposing, it is opposing the direction of the current flow. Okay, so that's how it plays the role, inductor. So it's pretty similar to resistor, right? Inductor, but it plays a role not only resisting, but it opposing the change in the direction. Okay, any question about these basic components, because these are pretty important. You are going to use it all your life when you become an engineer. Even software engineers use this. Okay, no question. That's good. Any question from our instructors here? Am I missing anything? Let me know. Oh, okay. All right.
Oh,
Thanks.
sounds good.
Okay. Thank you. Thanks. Okay. So let's look at how the capacitor looks like. So on the right side, this is like, let's say you go to the lab, you grab a capacitor, that's how it's going to look like. Most common kind. There are more kinds to it, but this is the most common type of capacitor. And the one on the left is actually when you do the circuit presentation, right? You're drawing a circuit, you will see that. So one is actual versus another is the circuit symbol. And by the way, I do teach in Ohlone College as an adjunct professor. I've taught almost 4 semesters there. So I have students there, they really like when we talk about, the microelectronics, because it's not only teaching you the basics of electronics, but you can relate to the, real life, right? Like, oh, okay, if I have to see a capacitor, you can actually open your, one of the maybe fire alarm or some of the, switch boxes, that we use for the carbon monoxide detection or something, and you can see resistor, capacitor, or the LEDs, So that's what my students kind of find it very interesting, this course. It's basic, right? But it has a lot going on here. We all have to know the basics to get into the next level. So this is how the capacitor looks like, and always remember the word capacity. So it's storing capacity, right? The next is our another favorite, resistor. Resists, right? It looks like that. You see all this red, green, and blue bands. Okay, this is how actually we measure the resistor. We will go into the details probably in another class. So those lines are just not for decoration, I'm telling you, even though they look kind of pretty, but they mean something. Okay, so those lines in the resistor. And then on the right side, you see that says this, like a wavy thing. That's the resistor symbol we use for when you're creating a schematic, right? What is a schematic? Schematic is when you do your circuit instead of drawing in a paper, you decide to put that in a software, right? And then you come up with the schematic of it, right? And in this like industry, you cannot have everything in a paper, right? It has to be in a schematic form so that you can generate some sort of logic out of your schematic. And later on, that logic you will put in your board and then you get the circuit, right? So, but everything comes from a scratch. Even now, after working for 15, 16 years, I start my circuit from a piece of paper, okay? And then it goes to the schematic capture. And then the inductor, you see here, it's a lead. There's two leads and it's a coil, right? Of, you can say some wires, right? And on the right side, you see there's two ways we will draw the circuit symbol of the inductor. And what's the difference? Again, just kind of recapping between the resistor and the inductor. That's why I put them together. It's kind of, they both kind of resist, right? But one kind of helps to switch the direction and other one just resist, right? So that's the main difference. Okay. Now let's talk about the most important circuit theory, okay? As long as you live, you have to know this. This is like, yeah, if you just know, let's say, um, we want to know only one equation today about the microelectronics theory, then I would just say, okay, that's it today, and we are done. So that's how important it is. It's called Ohm's law because this is showing the relationship between the current, voltage, and the resistance, right? Like I explained in the beginning, what is voltage? Voltage is basically from one point to another, you see some charge difference, right? And then that's how you know that there is a voltage that is happening at that place. But how you calculate that voltage? For you to calculate that voltage, you need to know the current that is running from point 1 to point 2 and what is the resistance, okay? And why I say the DC circuits only because the same reason, right? When it's a DC circuit means direct current, right? There is no change in the direction of your current. It's flowing in one way, right? So we are talking about current flowing in only one direction. Current, let's say, flowing from A to B. Current is never flowing from B to A. So DC circuits, we can always, and I'm talking a little bit about how you solve it. So let's say you want to solve for the current instead of your voltage, right? So you already know a voltage and you already know the resistance. Then using this equation one, you can actually find the current of that circuitry, right? It's the algebra. This is why we need the algebra here. So any question about the Ohm's law? So you see if the relationship is basically, if you increase your current, right, it will actually increase the voltage, right? And if you increase your voltage, it will automatically increase the current, right? So that's the relationship, proportional relationship of voltage and current in terms of the resistance that the wire carries, right? We have to know. And that's the Ohm's law, which talks about the voltage, current, and resistance relationship. Any question?
If you could some example of in terms of the circuit.
Yeah, we are having some example. Yeah, we'll have some example.
Yeah, that's good.
Yeah. So, and then let's see the capacitor. How do we know how much capacitance we have, right? So capacitor will store the energy in the form of electric field. If you don't like the word word electric field, you just can understand in terms of the voltage, right? We talked about the voltage. When there's a difference, potential difference. Potential difference is another way to say um, voltage, basically. So when you have two plates or two segments and you see there's a storage happening of the electrical energy, you also know there is a capacity happening, right? Like I say, capacitor quality. So you see that, and that's how you would calculate the capacitance of 2 points. You have to know the charge, which is Q. That's why we talked about all the notation in the beginning, right? Charge Q, and you divide that by your voltage, which is the potential difference, right? And that will tell you the capacitance or the capacity, how much, energy is going to be stored there. So in terms of calculating not the capacitance, but the actual energy, right? We talked about the energy. How can we know the actual energy that capacitor is storing? So that is our equation 3. If we want to know not the capacitance between the two plates, but two plates or let's say 2 points, you want to know how much energy can we save, right? Then that's the equation. You have 1/2 times the C is the capacitor value, right? Times V is the potential difference and square. So that's our equation 3. So there's a difference, right? Knowing the capacitor value is the capacitance, and how much energy it can store, that is the U, right? And the important fact is that when you see the charging and discharging of the current, that will flow, right? And once you have charged your capacitor fully, right, then there's no current flowing anymore. At that point, it cannot take any more of the current being passed through, right? Because it's already full. It's kind of like when you see your phone and you say, oh, battery charged fully, kind of like that, right? Okay. So some usage of capacitor, we already talked about it. You probably won't understand that much of the AC coupling or the RCLC, but the first two you can understand the usage, right? But I will share these slides with you in a little bit modified form. As you can see, like there's a lot going on in here, and I use this for my classes also. So next one is the inductance, right? So how do we know the inductance? How can we know the inductance in equation? If you know the voltage and if you know the dI over dt. What is dI over dt? dI over dt, if you know little bit of calculus, even if you don't know, I can tell you what is dI over dt. It's the change of current, right? Change of current, I is the current in terms of time, right? How much current is changing. So once you know from the 2 points, the voltage, and you know how much current change is happening, then you can divide that to get the inductance, okay? And that's your equation 4. And like I said, I will share the slides with the students who has attended, and so that, you get more enthusiastic about joining us next time. And it will be helpful for your classes in the school as well, I'm very sure. Okay, so more about the inductor and the AC current, DC current. I already talked about it. The AC current will, have the change in the direction, and direct current, which no change in the direction, right? And some of the application, DC current application is, for example, phone, okay, is our DC current application. AC current application, our dryer, okay. So those are some of the application, and you can, I mean, these are not hard to think of. You will learn as you go along more about the DC and AC current, and you see the application everywhere, right? But for now, in a very layman way, in the beginning, you can think of it as a, oh, okay, when there's a small amount of current that's happening, then like our laptops, our phones, we need a DC current, but a huge current, right? You see how the dryer, oh my God, when you're drying the clothes, you can understand a lot of energy happening, a lot of noise, right? That's the AC current, okay? In a beginner way. Trust me, the beginner way is always the way. I still think of my resistors as resisting, capacitor as a capacity. I still think that way. So, okay, quiz time. It's not quiz for you, but as I go along, I give you this answer because these are important. So I kind of summarized it, okay? So what's the difference between AC and DC? The change in the direction of current, right? And AC is alternating current, right? It changes the direction, and DC is moving only one direction. And what is the name of the circuit theory that relates the current, voltage, and resistance? Can anybody tell me? Anybody? What is that law called? The law starts with the
Is
O.
it
Ohm's law.
Ohm's
Yes,
law? Yeah.
Nabil. Yeah, that's correct. Nabil, you got it. Yeah, that's the Ohm's law. It talks about the relationship between the current, voltage, and resistance. That's right. Okay, so the next one is a true or false. There is a potential difference between in plates current, which creates capacitor capacitive behavior. I say plates current. I didn't say plates voltage, okay? Is that a true or false?
True.
No, it's actually false because it's not current. It is. The difference is, potential difference is always the voltage. So you have to
Oh,
see the voltage. So actually, it's already there. When you see there's a potential difference, right? So it's kind of a voltage creation happening, okay? In
okay.
which, yeah, so it's false. Okay. And then to find the inductance, L, voltage is divided by what? Do we divide that by change in voltage or change in current?
I think it should be change in current.
Yeah, it's DI/dt, right?
Mhm.
DI/dt means it's change in current. That's right. And what
Yeah.
is resistance? Thank you, Junaid. What is
You're welcome.
resistance are when voltage is 10 volt and current is 2 amps. So you have V equals RI, right?
Yeah.
V equals RI. From that equation, you solve for R. So if you know your voltage is 10 volt and your current is 2 amps, then what is the
Yeah.
resistance?
Yeah, I think like it should be like 10 divided by 2, like because the voltage
Yeah,
is
yeah, right. 5.
yeah,
5 watt.
5.
What is the unit?
Yeah,
Ohms.
it should be ohms. Yeah, 5
Yo.
ohms.
Yes, yes. Nice, nice. I really like the participation. Thank you. Yeah.
You're welcome. Thank
Yeah,
you.
so these are some of the important stuff. I mean, I didn't mean to quiz you all, but it's just, I think it
Mhm.
helps to kind of summarize. So let's go through the next one. I'm not going to go too much into the details, but this is how, if you have a more than one resistors in a circuit and they are in a series, right? You add all them up, R1, R2, up till Rn, whatever number, right? But if your resistors in parallel, this is the equation you use. It's 1 over the reciprocal of each of the resistors, okay? So these are some of the equation when you have multiple resistors in your circuit, right? Okay, now this is what Amin was talking about, like, let's say talk about a real circuit, right? So here it is. So this is our first figure for our circuit. You see there's 3 resistors here. We have R1 15, R2 20 ohms, R3 5 ohms, right? And then we have a voltage source of 20 volt, right? So first question for you would be, are all these resistors R1, R2, R3, are they set in series or are they set in parallel? Anybody?
So I think it is series. It's not parallel because the all the connected in like same circuit. because
Yeah,
parallel is
yeah,
like different.
exactly. Let's say if you take out that voltage source, right? You
Yeah.
take out the battery out, right? What do you see? All these wires are connected, right? And they have some resistance, right? All right. And then we're going to solve for V and I. But V and I, we cannot just solve for at once because each of the resistor R1, R2, R3 will have a different voltage, okay? So when we go back here, you see VR1, right? VR2, VR3. So we have to find each of these voltage. And for us to find each of these voltage, we have to know what is the current that is running. So now you can ask me that, Aziz Auntie, what we already know 20 volt. Why cannot we know that the voltage in the VR1 is 20, right? Because when you put a resistor, it acts like a resistance, right? So you will see some voltage drop there. So it won't be 20. It would be less than 20 in R1, okay? So first thing first, you will calculate your total R, which is in series, right? You add all the R and you get 40. And you use the equation, right? You know the R in series equation. And once you know that, you use the Ohm's law, which is I equals to V divided by R total. It's the, manipulation of that same formula, which is V equals to RI, right? And you calculate the current that is running through the circuitry. And in this case, it will be 2 amps, right? And once you know that, you can find, using that I, which is the 2 amps, you can find the voltage VR1, VR2, and VR3. So in the first case, right, VR1 would be what? VR1 would be 15 times 2, 30, 30. So that's how, like, each time you're going to see different voltage. Actually, I made a mistake. It will be half. It will be half. It's not 2 amp. And you know how I got it? Once you see here, because if you multiply that by, it cannot be 30, it has to be less, right? So if you multiply by half times 15, it will be 7.5, right? Did you understand the voltage drop here? Because it's gonna drop, right? So it cannot be more than 20. So that's how you're going to solve for all of the R1, R2, R3, whatever the voltage, okay? And once I share the slides with you, you should be able to, use this and go back to the circuit and use the Ohm's formula and find out VR1, VR2, VR3, okay? Okay, so I'm going to briefly talk about the KCL and KVL. Kirchhoff's law is, in one word, whatever current you put in your equation, and that's what you take out, okay? So let's say you, in your circuit, you are putting 2 amps of current. What you get out of that circuit? You get 2 amps of current outside, okay? And that's exactly Kirchhoff's law is. Kirchhoff's current law, KCL. You put 5 amps, how much current you are going to get out of that circuit? 5 amps. As simple. Kirchhoff's voltage law, you have a circuitry, you add all that, okay? And you are going to get a 0, okay? So basically, it's an example of KVL. If you see the difference, okay? E1 is 1 voltage, and how do you get R1 voltage here? R1 times I1, because V equals RI, right? You get all this voltage calculated, and the total voltage you will see in this circuit, which is E1 minus E2, right? One point to another, it will be all equal. That means the sum of the voltage in that loop is basically zero. I don't expect you to understand every single thing here, but trust me, when we learn something, even just a little bit at this high level, it will be so beneficial to you when you see it second time, okay? So the understanding KVL in one word, right? That whatever you put, that's what you get. Yeah, you put good, you get good. You put bad, you get bad. Just remember that way for the KCL. You put 3 amps, you get 3 amps. Yeah. And whatever the voltage inside a circuit, it all has to equal to zero. Okay. And the last equation, power. Power is voltage times current. Okay. So remember that that's one of the very important equation for the microelectronics. So I'm going to I'm going to take extra 10 minutes of your time. It's almost 3 o'clock. Um, and we're going to talk about our PCB tool and PCB. As you can see, the microelectronics is is probably, if I have to teach everything very nicely, what I have covered, I would need at least 3 hours, I would say. And we have only 1 hour. So, but trust me, it would be very helpful, even if you have seen it a little bit. So P equals VI, okay? Power is equal to voltage times current, okay? Let's talk about the PCB and PCB tool. So there's many PCB and schematic tools we have in the industry, and some are very common like a Cadence, Mentor Graphics, Altium. These are some of the design tools. And PCB can be multi-layer, and some simple ones could be like 2-layer, right? 2 metal layer, and inside 2 metal layer, you have the dielectric layer. What is dielectric? Dielectric is what? Dielectric is the semiconductor, right? It's not fully conductive. You learned yesterday. And when designing the PCB, right, other than you knowing the tool itself, you have to understand the component. And that's why we started with our components, right? Resistor, capacitor, inductor. You have to understand that. And some of the major PCB design elements, when we want to become a designer for PCB, like I am a designer, we have a lot of designer, we know, in Bay Area, actually, they all have to go through these first before they can come up with the design. You have to know your circuit schematic. You have to know the data sheet of each of the component that is being used. You have to know the design rules, how, how thick your wire will be, what would be the via or whatever you want to call it, drill, what is the size that connects each of the layers, right? And then, of course, the power planes. You can have in a design different powers, 5 volt, 3 volt, 12 volt. For example, currently I'm working on a design of a fan board, and this has 3 source of power, 3.3 volt, 5 volt, and 12 volt, right? So I have to generate separate planes for each. So all these are some, I say that's why some of the major elements that, you say like a must have, right? Once you start your design. And then those are must haves, but this is talking about the steps, right? We're talking about the steps here. So what are the steps? You have to place the components, your resistors, capacitor, inductor, and define the layers, or you can call it a cross section, and then do the routing, right? It's all in the software, but you have to know how to do it. There's a lot going on here. And completing the design with no DRC. DRC is a type of check. It stands for design rule check, okay? We have to have a no DRC error, right? Okay. And then finally, you generate the files. Gerber files, you send it to the fabrication home, assembly files, and then some reports like netlist and all that, okay? And then finally, this is an example. I put it on the side, some, you see on here some layers. You see top layer, bottom layer, some in between. You see VCC, all these power layers, right? And I have also some ground layers, You see there's some ground layers, okay? I wanted to show you. This is from an actual real life board. Actually, I was working on it a couple of weeks ago. I was so happy to finish it last week. And then quiz time again. When resistors are in series, how to find total resistance? Who can tell me? Do we add it or what do we do when resistors are in series?
Hello. I think add all the resistance individually
Yeah. Then
together.
you find the total resistance, right? Yeah. Okay.
Yeah.
That's nice. Thanks, tonight. And what
You're
is
welcome.
KVL in simple word? KVL. So KVL, Kirchhoff's voltage law, tells us it's not at all complicated. People think of it in a very complicated way when they say, "Oh, Kharkov." As soon as they're okay, then Kharkov sounds very complicated. The name, and they're like, "Oh, the law is also very complicated." No, Kharkov's law, both the circuit, current and the voltage, they're very simple. So just remember, or whatever voltage is happening inside loop, right? Inside my circuitry, they all has to equal to 0. Okay. And what is KCL? Kirchhoff's current law. It's the saying. Remember that saying. You put good, you get good. You put bad, you get bad. Your mind is empty. You're putting all good things. What comes out? Good. You putting all the bad things. Well, what comes out? Bad, right? So KCL is like that. You put 5 amps of current. You take out 5 amps of current. Okay. And what are some of the elements to design PCB? What we need to do? Some of the things we need to know. We need to know our components, right? We need to know our layers, how many layers we need. We need to know what kind of powers we need, right? Those are some of the elements. And can we know 2 major steps to design our PCB? Some of the major steps to design our PCB, can anybody tell me? Placing the component, right? Anybody? Yeah. So this is what it is, right? Routing, placing the component, defining cross-section, and finally having the design with no error so that we can generate our files, right? So those are some of the, major steps to design a PCB, okay? What is DRC stands for? DRC, design, rule, check, okay? Design, rule, check. All right. I wanted to talk about the maximum power, but it's pretty complicated as I feel we have to learn one more theorem, and that is called Thivian theorem, right? And Thivian theorem is actually, I would say, it's not hard, but it's a lot more understanding than KCL, KVL, and Ohm's law. So if we know the Thivian theorem, then we can calculate the maximum power, and that would be our next session, okay? And thank you, everyone. Please let me know any questions, comments.
Okay. Amin, any questions? He's one of
It's a
our.
great class, Apu. Yeah, thank you so much. Yeah, it
No,
was
thank you,
very easy to
Amin.
understand. I think it's good for
Yeah,
high school student. Yeah, that's
yeah,
nice. Thank you.
No, our students are nice too. I'm very glad
Yeah,
they're going to be, great future engineers. I can tell, right? You know, these things are pretty intense, and at this level, like as a high school students, they're showing interest, and I'm very sure they will be, with the grace of God, they will do very well, Yeah.
yeah.
Yeah. So thank you, Ridwan. Thank you, Nabil and Junaid, everyone. Thank you. And I will be sending an I mean, thank you. Yesterday, your class was very good too. Thank you for teaching with me this fall. And inshallah, we're planning, maybe not in winter. Winter people goes out for vacation and all that. Maybe in spring, we are thinking to have more session for classes, okay? And we love to see you all back in spring again and cover more of the fun part of the hardware engineering. Yeah. So, having said that, thank you, everyone, and we'll catch up soon. And I'll send out some of the slide contents to you in the email. Okay. Any
Yeah.
question? Any question? Thank you. Any question? All right. Thank you, everyone. Thank you.
Yeah. Thank you all.
Yeah. Thank you. All right.
You're welcome. Thank you so much for sharing this valuable information. Thank you.
Thank you.
Bye.